Continuing on page 172, we'll look at the next thing, which is called the uniform continuity in the middle of the page. It says definition 9. The function f of x is uniformly continuous in a closed interval, means that given any epsilon, there exists delta such that for all points that's within delta of each other, okay, then f of x will be within epsilon. Now, the normal definition of continuity says that when we have a fixed point, okay, and any point that's away from that fixed point within delta, then f of x will be within fixed point within f of x of that fixed point. That is fx minus fx0 is within epsilon. At least that's what I think continuity is proof, something like that. But the point is, well, it'll say what it is right here, okay? So in this case, instead of some fixed point and then considering its neighborhood, that is, we consider each fixed point in the domain, we are now going to consider any 2 points, okay? So we're considering 2 points at a time instead of 1. So any 2 points, as long as they're within delta distance of each other, then their correspondent f of x, it will also be within epsilon of each other. If that is true, we call it uniformly continuous. Now, on a closed interval, uniformly continuous and continuous are the same thing. That is, one imply the other. Now, generally speaking, I think uniform continuity always basically implies continuity, because you can let the one of the points be the fixed point. But continuity, however, doesn't necessarily imply uniform continuity. That is, but however, on a closed interval, it does. So uniform continuity is a more stricter requirement than continuity in terms of being continuous. That is, it's continuous and it can't take off too far, okay? If it takes off, then it's still continuous, but it might not be uniformly continuous anymore. And we'll see an example of that later. Right now, we're going to show that on a closed interval, uniformly, any continuous function is automatically uniformly continuous. Now but first, before we do that, we're going to give you a counter example. That is, if your interval is not closed, specifically if it's open, let's say for example, the function 1 over x in 0 to x to 1, is continuous from 0 to 1, okay? Being that the 1 over x looks like this, right? Here's the familiar picture of 1 over x. Is continuous from 0 to 1. Here's 1, here's 0. But that's because it doesn't ever reach 0. But you notice that the difference between f of x is getting bigger and bigger, okay? It's not being controlled by epsilon. And to prove that is we can actually prove it. That is, we can do f of x minus f of x prime plus delta. So let me show you my notes. So for the function 1 over x, let's actually calculate the difference between f of x and fx prime, okay, some point, and x prime plus delta. What is the difference? And let's examine what this difference is. That is, if delta is a little bit away from x, what would be 1 over x minus 1 over x prime plus delta? Now, we do the common denominator trick, and very soon you notice this value equals to delta over x prime times x prime plus delta. And where does this value go as x prime go to 0? Okay, and then this whole thing goes to infinity. That's because the difference of these two, the difference of the values as x gets approach 0, as you can see, the difference gets bigger and bigger, and as x goes to 0, because then it will be equal to delta is fixed in this limiting situation. So say delta is 0.1 or something, and while x is approaching 0 fast. So then then this whole thing will be equal to delta over 0.1, basically. times 0.1, and that is well, delta is 0.1, and 0.1 divided by some x times x, that is going to 0, so that is going to be, that's going to go to infinity, and that's why the difference is unbounded. In other words, we're not going to be able to find some epsilon to limit it on. Okay, and so and that is. So that's a counterexample. Now, having said that, let's consider theorem 8. So next, let's look at theorem 8 on page 172, where f is continuous will imply directly that f is uniformly continuous. Okay, remember, uniformly continuous already imply continuous, but now we're gonna if f is in a continuous and in a closed interval. Okay, the closed interval bit is on the other side of the page, so you might miss it, but it's crucial. If f is continuous on the closed interval, then f is uniformly continuous. Now, so let's look at the proof. The proof is, first, the function f is only defined from a to b. So anything that's less than a or bigger than b will simply define it as f of a and fb. That way, just like we did in proof of theorem 6, just so that f is a continuous function going from negative infinity got to a, all level, and then it moves around and then got to b and then stay at b to positive infinity. So then we don't have to worry about the domain. So then, having said that, then given epsilon bigger than 0, okay, then for each point that is c is any point between a and b. So given for each point c, there exists a delta which is based on c, such that f of x minus f of c is less than epsilon over 2. Now this is, the epsilon over 2 is the same for each c, okay? But each c will have its own delta. In other words, we have, so each c has a little, each point, okay, has a little interval such that if x is within delta of c, then f of x will be within epsilon over 2 of f of c, just like the definition of continuity. Now, so what that means is each delta then helps us define a little interval around c, right? And where it's and it's a covering of the point c, and together we're defining this for all of the c's from a to b. So together we have a covering for this thing So by theorem 5, the covering theorem, it says that if you have a cover of a finite, of a closed interval from a to b, then if you have such a cover, then it is possible to pick a finite number of your covers to cover your entire closed interval. Now, we apply that here. That is basically the power of this whole proof, okay? Once we apply that, so now we end up with a finite number, that is IC1 to ICN. That is, we have a bunch of numbers between A and B, C1 to Cn, which are where their covers, okay, is able to cover the entire A to B. With nothing missing. So we have a finite bunch of points and the finite covers that they own. The covers are not all necessarily the same width. Some are narrower, some are wider, but they all work. And so all these covers then together will end up covering A to B, and I will show you a picture of it. Okay, this is the same picture I showed you before. Now there's some covering, right? I picked up a bunch of points, C1 to Cn, okay, or something, which I did not draw here, but these are each line is their covering. All right, so you notice that all of them together ended up covering A and B. Now, there might be repeats. I didn't in the process of saying that there exists a finite number, I never said the finite number can have a ton of repeats. That is, some points might be covered by many coverings, right? And end up being covered. So in other words, there might be a lot of redundant covers, but that's okay. My whole goal here is just to say that there are a finite number of covers. So here's the original covering, okay, and as you can visualize it, some covers are longer than the others. Some might be completely contained in a different one. None of that matters. The point is that is finite. All right, so let's keep. Now that you can visualize it, let's keep going. Now keep going on page 173, where there's a new concept. Okay, now the endpoints of each cover, each short little slice, so they each have an endpoint. Now the endpoint of each cover is what are they doing? Will form a subdivision of A to B. Because the endpoints, they either coincide or they don't, but there are finite of them, which means they cut, you have various endpoints along the thing, but only finite number of them, so they're going to form a subdivision, right? They just cut A and B into a finite number of stuff. Okay, now before we go any further, now the book doesn't say this, but here's what I want to do. Okay, now to keep things a little clearer. Now before we get to the finding our subdivision, I want to remove any cover that's redundant. That is, if there's the number of covers is limited, right? Is finite. Okay, so then so let's look at each cover and go through a process of throwing away anything that's redundant or extra. And here's my plan. Okay, that is I want to throw away. Let's see. The camera is focusing on the wrong thing. Yeah, it's focusing on the image. Well, I guess that's sort of okay, I suppose. Anyway, let's see. So what we're going to do is we are going to remove any cover that's contained in the combination of the next covers. That is, we'll say start with the first one, the red line. Okay, that's by itself. It's not contained in anything, so we'll keep it. And then look at that bluish line or purple, whatever that is. So that one, that's already contained in the other two, so we throw that one away. And you keep doing that. So that we don't. So you see, this is the same as that one, except that it doesn't have any redundant ones. That is, each cover isn't already included in something else. That way, we don't have so many covering. So this I added extra process just so that we can think of it better. Okay, that we have. Oh, I see why it's so dim. It's because my screen darkened. There, how's that? That's much better. All right. So then what happens is that. So as you can see, each point is inside one or two coverings. Okay, two at the most. Most of the time, like look at X prime and X double prime, they're in one cover, right? And the one over here, the X prime over and X double prime, one of them is in one cover and one of them is in the other cover, in two covers. And then see the little vertical black lines, those are all the subdivision points, because those are all the endpoints of the various covers. So we have a finite number of black lines, which forms a subdivision for this for interval AB. All right. Okay, so next we are going to, with my simplified covering set, then we'll continue doing what the book does. What the book says works even if you don't bother with throwing away extra junk. But it makes the thinking much more difficult, because then you have to worry about, how many covers are in there, is being multiplied that. Anyway, and throwing away extra junk clears, basically like cleaning your room. It makes everything a lot easier to find or notice. So I did a bit of housekeeping, and then but now let's continue. What we're going to do is choose the number delta as the length of the smallest subintervals into which this was divided. Now, at the beginning of the proof, we have mentioned that for each delta, you see, we are given epsilon bigger than 0. So epsilon is fixed, okay? Then if for each of our subinterval has a delta, right? Such that this relationship holds. So we have a finite number of intervals, which means we have a finite number. They are made up of finite number of deltas. Each one has the length of 2 delta C. Okay, so we'll find that being that we have finite, we're able to find the shortest delta, that is the smallest delta or the shortest interval, and we'll call it, the shortest delta C will now be given the name delta. All right. So choose the delta that as the length of the smallest of the subintervals into which the interval AB was divided. All right. Now let's x prime and x double prime be 2 points, any 2 points such that x prime minus x double prime is less than delta, and which is what I have pictured here. Okay, and let's see. We have see, there is all these vertical lines where a subdivision. So we pick delta as the delta is the 2 delta is the width of any interval, right? So we'll pick delta to be the smallest one of something. This delta seems to be, I draw it, might give the wrong impression. Let me think. Okay, I said something wrong. I just now said that let delta be the smallest of the delta C's. No, that's not the delta we choose. We often choose that one in most proofs, but not this case, okay? And let's repeat what the book says. Let delta be the smallest, let's see, where's delta? Define delta as the length of the smallest of the subintervals into which the AB is being divided by the subdivision. All right, so my picture is correct. So here's my subdivision, all these small black lines that goes down, and delta is, pick the one that's the smallest, because we have only a finite number of subdivisions. So delta is the smallest distance between those vertical black lines that we can do. Okay, so, and also my picture says that too. All right, so if that is the case, then if we force x prime and minus x double prime is less than delta, then what that means is that there will be at most one subdivision in between them. Okay, and they're always covered by they're inside, and then also they're both inside a single cover. So because the subdivisions the intersection of subdivision has 2 covers, right? And so if they are within delta, where delta is the smallest between the subdivision, then they will always be inside a single cover, like this case, where it's inside that green cover. This case, that they are both inside this yellowish green cover. Okay, and so that's continued reading. Now, it is clear that there can be at most one of the points of subdivision between x prime and x double prime, being that their width is less than the smallest of the divisions. Okay, and both x prime and x double primes lies in a single one of the intervals, such as, let's say, ICK, and as a result, then we have this thing coming out. Okay, so we have f of x. Now we're going to calculate f of x prime minus fx double prime. What is that? Then they're in the single interval, right? ICK, which means being that they're both in the same single interval, their difference is less than or equal to, this is the triangular inequality of absolute values. So it's less than or equal to each one's difference from CK, and each one's difference from CK is going to be epsilon over 2, because that's what we said before. Okay, in our over here. All right, so as we said before, given epsilon, we have the situation where fx minus fc is less than epsilon over 2. That's how we defined our ICs. So all our i's are defined that way. So as a result, then we're up here, and then these two things are both less than epsilon over 2. So together, f prime of x minus fx double prime is less than epsilon, and that concludes the proof. All right. Now next, let's read this part where the uniform continuity. So far, we have proven it for a function of what is this? One variable, I think. Yeah, but we can extend it to functions of more variables, such as the function of 3 variables, and we define it the same way. That is, if x is within delta of some point, y is within y and some other y is within delta, and z and some other z is within delta, then the f values of the difference of the f values is less than epsilon, then the function will be called uniformly continuous. And if it is, then a similar theorem, similar to theorem 8, except that now it has 3 variables, is also works. That is, ordinary continuity in a closed bounded region in 3 dimensions implies uniform continuity there. Okay, and the proof is similar, but we're gonna skip it for now because right now we'll just stick with the 1-dimensional job. Okay, and that's that. So next, we're now on page 173. Please look at Duhamel's theorem, which is something we've done many times by now, okay, without having proven it or even seen it. We just refer to this future page and used it. So now let's actually see how it's proven. So theorem 9, let's first read the theorem, okay? And the theorem 9, f and g both continuous in the closed interval, okay? The closed interval is on the other side, but don't miss it. It's a closed interval. And then alpha is going up, that's fine. And then we have a subdivision of called triangle of A and B. So the triangle, which is called delta, is the subdivision, xk, from 0 to n. And then we have 2 numbers, psi and eta, such that psi of k is, and both psi and k and eta of k are in each interval from k minus 1 to k. All right, and they could be endpoints, we don't care. And so if that is the case, then the Duhamel's theorem, as we are fairly familiar with by now, is that the limit of the sum of f psi g eta, notice the different points here, okay? Alpha k and alpha k minus 1 is equal to this integral right here. All right, so that is what we've been taking for granted that we're going to prove right now. But before we start proving, let's figure out what it means. What is this thing? How does this thing relate to this? Now let's look. Well, we know it by now, but let's look at it again on page 151 and refresh our memory as to exactly what that means. So here's 151, okay? And what is the Stieltjes integral is defined as this particular limit with psi of k in there, okay? If you have 2 functions inside, but it uses the same psi of k, then it's the same as one function, right? It's only the Duhamel's theorem is different because it says you have this thing in there, f, and then some other g of eta of k. You know, a different thing which throws a wrench in this thing, and that's why we have to prove it. And prove that it's okay, even if the other number is different, everything is being squeezed into, see, the delta is being squeezed to 0 anyway, so it works out. But we have to prove that separately. We can't just say, oh yeah, it looks that way. So this is sigma delta. In the meantime, sigma delta is defined as this sum. That's inside the limit, okay? The exact same thing. Just want to remind you what sigma delta is that we've been talking about this whole time, but doesn't hurt to go back to look at it. Okay, so now that we're done with that, let's go back to page 173 and read our proof. Now we're gonna set sigma delta prime, okay, equal to the sum on the left of the equation 6. So this one, okay, being that this one is different from the regular one, then we'll call this the prime one. Okay, so the regular one with just with the same thing on the inside, which is not written here, we'll call it sigma delta, and this thing, it has a psi k and eta k. We'll call it sigma delta prime. So it will equal to this sum right here without the limit. All right, and then sigma delta then equal the same sum equal to this thing, except that for sigma delta, that's the regular one, where eta and k are the same. So it will be eta equal to k. All right. So what do we have then? Then the book doesn't have it written out, but I do. Okay, so now we look at it. So what that means is sigma prime, this is sigma delta, I don't have the deltas written here, but the prime one, that is the one with two different things inside here, sigma k and eta k or eta. Did I say, what? This thing is called psi, sorry. This is sigma, this is psi, this is eta. Okay, or eta or something. Well, eta. Let's call it eta. Anyway, so this thing is this one, this summation. Okay, go all the way there, right? And then with a triangle in here that I ignored, and then this sigma with nothing on it, and that will be the original one where the function where they are the same. See, both have eta k in there, so you can pretend that this is one function because they both have the same argument. So that is what this subtraction will end up being. Maybe I should write down the triangle too, just to be consistent. I'll go write it down. Okay, I got my triangles. So now we are, okay, that is what that is. And so far so good. So bear in mind that this is the new one, okay, with a very different psi and eta, whereas the other one is the old one where you have only one variable over here. So that's the only difference. Having said that, let's see what the book says next. Next, we have, so it says, let sigma prime equal to the sum to the left of equation 6 and just sigma equal to the same sum, but with eta equals to psi for all the k's. Okay, the next sentence. Let epsilon be an arbitrary positive number and let delta be the number which correspond to it according to definition 9. What does that mean? Well, it says following definition 9, so we're going to read definition 9 again. Definition 9 says, for uniform continuity, the function f is uniformly continuous in the closed interval, means given any arbitrary epsilon bigger than 0, there is a delta such that all points that are within delta of each other will have the function values will be less than epsilon. Okay, that's the definition of uniform continuity. All right, so now that we know that, let's, what does that mean? I have this written down here. Okay, and so basically, let delta be if x prime minus x double prime is less than delta, then fx prime minus fx double prime is less than epsilon. I'm missing an f. All right, I added f back. Okay, so that's our condition. That means that this function right here, we're calculating this difference right here. Okay, so the same thing here, we continue calculating. That equals to, right now we're going to do a bit of algebra. So we have f psi k g eta k, and then over here f eta k g eta k, right? So we can factor something out. That is this part is common. So we factor out the f psi k minus f eta k, and the rest is the same. So we got to this formula. Okay, so f psi k minus f eta k, remember psi and eta are both within the xk and xk minus 1. Okay, so then as a result, then they are both within delta, right? Because the subdivision is, let me make sure. So what we're going to do is first I should mention that we'll choose the triangle to be less than delta. That is the maximum of the subdivision distance, x prime, and that is the distance between xk and xk minus 1. The maximum one, which is the triangle, has to be less than delta. If that is the case, then f psi k and f eta k is less than epsilon. Okay, and that's where I got this equation. So this then goes down to this. We can factor out the epsilon, so we end up with this stuff, which then the next step is then we maximize g eta k, which can be done because g is continuous on the closed interval, and therefore it is possible to find it reaches its maximum. It has a maximum. Okay, it has a limit. It's bounded, in other words. So this will be less than the maximum of g on anywhere. Okay, no matter what the g anywhere on the entire interval that we're talking about. So that, and then we have only the summation sign then has only this stuff left. And that stuff is just alpha b minus alpha a, as we have done several times. And because of the telescopic situation, and once you add up k from 1 to n. And as a result then, which means this thing is less than epsilon times some number, which means these things approach each other, okay, in the limit. So as triangle goes to 0, the sigma prime is going to be equal to sigma. And what is sigma? Sigma is exactly the integral of ab fx gx dx, as we have seen in the definition of the integral. Is it dx? And it should be d alpha x. Let me fix that. Right, on the following page, as your book says, okay, A equals to d alpha. Then the limit of these two sums are the same, and then we have now completed the proof. So the proof depends on the uniform continuity principle, which works out very nicely at restricting the change of f. So f can't go very far. It got limited by epsilon, and as a result, the whole thing converged very nicely. All right, so if alpha x equal to x, then we have just a good old Riemann integral. So that's the regular form of the Duhamel's theorem. And so the next thing is, next we will work on theorem 10. So next, let's look at theorem 10. Now, theorem 10 is some kind of an expansion of theorem 9. Theorem 9 was a product of two functions. Then we're going to stuff in a slightly more complicated function into theorem 9 to make it work for more situations. So here is theorem 10. Let's read it. It says, let's say we have f of x, y, and z, which is continuous on the closed interval. Don't forget the closed interval on the other side of the page. Okay, sometimes it's easy to miss it when you're just reading. Your eyes are focused here, but closed interval, I think they should have moved this like at least over here. It shouldn't be clear back on the back. But anyway, this is very important, and it's a closed interval. We're not talking about open intervals here. So f is in a closed interval and it's continuous. That means it's very limited, bounded and stuff. And then alpha goes up, okay? And xk is some kind of a subdivision. We cut AB into a bunch of chunks. And then, okay, so this subdivision works for x, y, and z, okay? So we're using the same subdivision, all right? Because x, y, and z are all bounded by the same thing from A to B. That actually matters, okay? Remember that x, y, and z are all happen to have the same range, only from A to B. All right, so having said that, then xk minus 1, there's 3, now we have 3 of those Greek variables, psi of k, eta of k, zeta of k. All right, so all 3 things are in between xk minus 1 and xk could be endpoints. And then, so then we have this particular situation happening. So then the integral, limit, and this is not even the integral, this is just a definition. The limit as the triangle goes to 0 of the sum of f with 3 things changing in there, okay, 3 points, but the alpha is the same, then it will be just the integral of all 3 things end up being the same, okay, just like the story before, where the sum of 2 things, okay, end up with the same x. So the 3 things, we have 3 things here, it will just end up with xxx and then d alpha x, and that's the theorem. Now, next, let's look at the proof. The proof says, well, f of x, y, z is uniformly continuous. Okay, then we will use the same proof as we did the previous Duhamel's theorem, and say that now then with the same deal, the sigma triangle minus sigma prime triangle, okay, which just like we did before, we have this thing subtracting, and with alpha xk and alpha k minus 1. And what is this? This thing is going to be less than epsilon, okay, just like the previous proof with the same idea. When we have, in the previous proof, we have the f is in here, okay, psi k and eta k, they're different, but they end up being inside epsilon because f is uniformly continuous. And so this, we are pulling this, the exact same trick. The f psi might be all, f is like there's psi k, and then, well, the first one is the same, but the second one's all different, but that means nothing. Okay, they're all within that range, which means by uniform continuity, these two values has to be less than epsilon times that, which is epsilon times a fixed number, which means this limit is going to 0. I mean, this difference is going to 0 as epsilon goes to 0, and meaning that the limits are the same, and their limits is equal to exactly this thing right here. And well, just like this situation, okay, the exact same story, and that's how we prove theorem 10. So now, as an example of theorem 10 that we just proved, let's look at example A. Okay, now to look at example A, it says consider the limit of section 1.1 in chapter 3. That is on page 89. All right, and which I will show you right now. Here's page 89, as you can see. Wait for the camera to zoom in. Why is it not zooming in? Let's cover the screen a little more. Okay, the camera is not zooming in. Give me a second here. I will get it to do. Okay, so there it is. So the limit right about here, okay, L equals the limit sum of all that stuff. See, we have psi and then eta and then theta, where we have x1, x2, and x3, which is the where x is the vector. Okay, this is chapter 3 was talking about vectors. Imagine those good old days. And then times the difference, ti minus ti minus 1, and the whole sum as some kind of a delta goes to 0 is the, we're calculating arc length, I think. Yeah, it says so right up here. But anyway, so take a careful look of this thing, and then we are going to use the theorem 10 to prove this. So coming back to page 174, we have, we'll define f of x, y, z equals to that same L, okay, where we have prime, except that we're going to stuff the x, y, and z inside the parentheses here. Now, at this point, you notice there's an x here, and there's another x there, and are they related? And it doesn't look confusing. The answer is no, they are not, okay? The x outside is a vector, and the x inside is the variable for f. So to avoid the confusion, I decided to change the vector's name from x to u, like this. So then, so let's look at this. Okay, this is the original form where we have x prime. Blah, I copy this from page 89. Okay, the original definition. Now I'm going to change the x to u. That the vector x, let's call it vector u because we have an x here and we don't want the two x's to be confused because they have nothing to do with each other. So now we recall L as the limit of u prime psi 1. Psi I, and then u2, and then u3. Okay, and we still have a keep it on t for now. We're going to later change the t as well. So then we're going to define f as the square root of u prime x squared. The squared applies to the entire u prime. Okay, and then u prime 2 y squared and u prime 3 c squared. So that is, so now as you can see, there's no confusion here. Okay, there's no confusion of too many x's because x has nothing to do with u. U is just a vector for which we're measuring the arc length for. So that is pretty good. As I even have an example what such a function f might look like. For example, let's say our u of t, our vector, is sine t cosine t t squared, as we have done many times, right? I just made that up. So then u prime, of course, then becomes cosine t minus sine t and 2t. Then the function f, as defined by this, will be plug the x into t for the x position, right? So and then we have to square it. yeah, it's squared. So the first, this thing squared with x in it instead of t. So the function f then is defined as cosine squared x plus sine squared y plus 4c squared. Okay, that would be this is just an example of what this might look like. And sometimes the notation can get confusing, and when it does, it's helpful to make up an example for yourself so you can see what's going on. So in short, the function f is a 1 degree function that has with 3 variables, right? It's it's just a regular function of 3 variables. It's not a vector function or anything like that. All right. So now we will, that's just an example, okay? So that is, now continuing, we will say that the square root function is continuous as long as for the stuff that's inside the square root is bigger than 0 or equal to 0, right? It's continuous all the way up to 0, and then flips out. So then, our vector, the u of t, is continuous, and it belongs to C1 in fact. Therefore, any function we make out of these two operations, like f, which is defined out of those two things, right? F is defined by the square root function and the original vector function. So the f then, where's my f? Right here. So then f is continuous on the closed interval. Then we let alpha x is just x in this case. And then, so now we're going to plug into theorem 10. By theorem 10, the L, okay, which is the limit of f psi eta and theta of xk minus 1 is going to be equal to this, which is AB of f xxx. That is what theorem 10 says. And then we'll plug f back in there with x being all 3 arguments. Okay, so fxyz, which is right here, now is with x in all 3 arguments in this equation. So then we have the integral of x, right, dx, which is exactly the answer, which is this. Okay, then that's the magnitude of the vector u of t, which is x of t, and that's how we got this. Did I write that down? Yeah, I did. Because that is, well, let's see. Oh, right. Because well, the book wants it to be in t form. Okay, we change x to t in the integration argument. So then it becomes this should be dt. Give me a second here. So the arguments of integration. Well, this is the answer, but the book likes it to be in t, so we'll change the argument of integration into t. It doesn't matter what you call it, right? T, x, it all integrates the same way. So that this function then, it becomes the t. I changed all x's to t's in this equation here. So it becomes the t, and then that will be equal to this. So it's basically the vectors, the integral of the magnitude of the vector, which is this thing, okay, square root plus, of the sum of the squares from a to b ut of dt, which is just what the book has in right here. See, where x prime, the book goes back to x, okay, so then it's x prime of t dt, and that's why this integral end up being this integral. There's nothing really difficult about this example except for the notation. Just the hard part is just keeping the notation straight. So I'm going to show you this page again. That is the entire thing. Yeah, it is. And let me level it there. And so then you can look at it more carefully. All I did is just change the name of some variables so that everything looks better or clearer, let's just say. And of course, it's longer this way. But so please make sure that this is clear in your mind, okay? Don't get thrown off by the variables. Like, what are we calling stuff? Doesn't matter what you call it. The theorem works the same way. Next, let's look at the bottom page 174, where we're going to prove the intermediate value theorem. That is what I call the river crossing theorem, okay? Well, let's say you are between A and B. Here's the river, right? And you used to be here and you got here. How'd you get there? The argument is you must cross the river at one point. Okay, you have to, well, somewhere you gotta cross it. You might say, well, I can fly over it, ton over it, jetpack over it, or jump something. Even then, you have to do it at some point, right? You have to jump over here, or tunnel over here, something. You got to cross the river. You can also argue that I can just beam myself over there. Beaming is not allowed. All right. So then you have to cross the river, and so that is what the intermediate value theorem says. If f of x is continuous in a closed interval, right? And if fa fb is less than 0, that means they have different signs. Either fa is positive, fb is negative, or vice versa. Then f of x equal to 0 at some point for some x that's inside a and b. In fact, the x is not even the endpoint. Okay, the x is in between. Now, suppose that isn't true. If that is not true, then it's not the endpoint. Well, that's actually for obvious reasons, because we already said fa and fb multiplied together is less than 0, which is not 0, which means neither of them, one of them can be 0. So that's all the reason there is. So anyway, so in some point inside of a and b, not on the edges, then this guy has to cross. You got to cross the river somewhere at big X. Okay, some big X, you cross the river. It could be here, 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 anywhere, but you crossed it, and because you got from here to here somehow. And then now suppose this isn't true, that you have to cross the river. Then in other words, that fx is not 0 along the entire river. Okay, it's just never 0. If that is the case, then we can define a function called 1 over f of x, right? I mean, the denominator is never 0, so well, good. And such a function would be continuous on this whole thing. And now it, including the endpoints. Therefore, it fits, in other words, it is continuous and uniformly continuous because it is continuous on the closed level. All right, and so what does that mean? It is bounded there, okay? So the function isn't going to go nuts on you. And so now given epsilon, okay, some arbitrary positive number, by uniform continuity, there is a sequence of points between a and b such that the variation of f between any consecutive pair is less than epsilon. Now the sequence of points, where do we get the sequence of points? That's from, let's look at the previous page, theorem, in the proof of theorem 8, okay, where we have, remember, if we were giving epsilon, then the whole interval can be covered by this is the sequence, and that's the series of points. Those are the points inside the cover, right? And so we have a series of points because we have a finite cover being uniformly continuous. So there's a sequence, meaning finite sequence, I believe, between a and b such that any consecutive pair of such that we are given epsilon, there exists each point is some kind of a delta such that the function f of x between any consecutive pair is going to be less than epsilon. That is, we're repeating this argument right here. See, as long as this thing is created such that as long as x, where's my x? Right. As long as x is between minus delta and plus delta, then f of x, the difference between f of x is going to be less than epsilon in that interval. All right, so having said that, that means, so let's keep reading. Now fx has to change sign at some point, at 2 consecutive points of the set. So at some point, it has to change sign in the same interval, okay? Okay, give me a second here. So let me show you my notebook. We have, as I mentioned, we have given epsilon bigger than 0 by uniform continuity. We have a limited number, a sequence of x's from where x1 is a, xn is b, and there's a limited sequence that corresponds to the finite number of covers, such that in each cover, fxi and xi minus 1, so xi and xi minus 1 are in the same cover. All right, each one is in the same cover, and it's going to be less than epsilon. Now, if that is the case, then f of x has to change sign at some point because fa is less than 0 or bigger, doesn't matter. Fb, at some point, the sign will be different. So it has to change sign among these finite at some point, okay, between two consecutive points. So it could be change sign between 1 and 2 or 2 and 3 or whatever, but it's got to change sign because there's only finite number of these things. Okay, so if it changes sign, like right here, see, there's epsilon, and here's x f I minus 1, and then it changed sign to xi. I minus 1 to fi, its sign got changed. So then what that means is that and then epsilon is going to be bigger than the difference because that's what we presumed, and that is even that's xi minus xi minus 1, okay, and which is bigger than, which is less than xi minus 0, and that is fxi, and that means that since fxi is less than epsilon, then 1 over fxi is bigger than epsilon, which means 1 over f of x is not bounded, okay? Because it can be bigger, it's supposed to be smaller. Sorry, I wrote the sign wrong, that's why it looked weird. Okay, it should be bigger. See, epsilon is bigger than this, continue to be bigger, and being that this is negative number, this is bigger than this, which is fxi. Is that right? Let me double check some more. Yeah, it's fine. Now we have, so the distance between fxi and fxi minus 1, remember one is positive and the other one's negative. We just, we assume one of them is positive, the other one's negative, okay? So that their distance is less than epsilon, so the distance of them from 0 is also less than epsilon. See, that's what my picture is for. Okay, so this is going to be, this value, if one is positive, the other one's negative, it's going to be bigger than or equal to this value minus 0, which is just this thing itself. So each fx, so the fxi that went from negative to positive, let's say it went that way, then is less than epsilon, which means 1 over that thing is going to be bigger than epsilon. And being that our epsilon is arbitrary, that means this thing is not bounded. Okay, and that is a contradiction. So that's how we prove the intermediate value theorem. Okay. Now the intermediate value theorem says something about fx equal to 0, but if it has a cross at 0, the 0 river, but if the river is somewhere else, as long as in between these two guys, right, or the same guy, these two locations, the principle works the same way. And we're going to prove that fact in one of the homework problems, problem 11, I believe. Well, you're going to do that, okay? And that would be the general intermediate value theorem, which says that f is able to achieve every single value between fa and fb, or between its max and min, something like that. And we'll do that in the homework. So next, let's go to page 175. Where there are some critical remarks about the least upper bound. Now, so please read the remarks yourself, okay? They're quite interesting, although we are not really concerned about them right now, which is why they got stuck in some remarks. They're concerning the least upper bound and whether it exists or not, basically. And so, but at this point of our studies, we just assume the least upper bound exists. And now that's in the real number system, that is. Now, so let's go down to reading this part of the paragraph. Now the characterization of the least upper bound is given as this, or definition, okay? Given a set E of real numbers, you have some numbers there, okay, E, and the E has an upper bound A. So let's draw this out. So you have let's say a bunch of real numbers. So we have, a bunch of real numbers. We'll call it E. E isn't the line, it's just the dots on the line, okay? So you might have a bunch of dots. They're not even or nothing. And anyway, and they have an upper bound, a least upper bound for that matter. The least upper bound, we'll call it A, okay? We'll draw it right here. Here's A. that's their least upper bound. So there's no bound that's any smaller, okay? And so the points E get closer and stuff. So what does that mean? So given epsilon, okay, if you have any epsilon that's given, then there exists at least not a number A of E such that A is bigger than big A minus epsilon. That is, if any distance of epsilon, let's draw a small epsilon here. Here's my epsilon. Okay, so this point, this line right here will be A minus epsilon, right? This A minus epsilon. Any epsilon that you draw, so I have A minus epsilon, then there corresponds to at least one number of E where one number A of E, so there's an A in here, okay, where A is bigger than A minus epsilon. So A is somewhere in here, and it's bigger than this line, because A is the upper bound, right? So anything less than the upper bound is, any line that's less than upper bound, A minus epsilon, no matter how small epsilon is, then you will be able to find something that went past this line, because that line is below the least upper bound, right? So something better be over it. Otherwise, that would be, if there's nothing here that belongs to E, that means that thing is the new least upper bound, okay, which violates the definition. So anything less than A, by even a tiny little bit, you'll be able to find members of E in here, is what this sentence means. And also, the next convention that we need is if a function is unbounded, you know, like it goes to infinity, like the power, like the function x squared, for example, then we will call the upper bound to be positive infinity. Okay, and similarly, any function that takes a dive to negative infinity, we'll say is bounded below by negative infinity. That's just we'll just call it that. It's not really bounded, but we'll call it the bound as negative infinity or positive infinity according to the situation. So we have finally come to the end of this section. It's quite long, right? But it's a very interesting and important section that deal with the real number system, continuity, boundedness, maximum intermediate value theorem, and Duhamel's theorem, and all those lovely theorems. So it's a worthy pursuit. So please do spend enough time on this section until you understand every bit of it perfectly. So with that, let's do homework. For homework, which is on page 175. Please do problems, found it, problems 1, 2, 3, 4, and specifically problem 1, do this, make a smaller interval, not the bigger one. A bigger collection. Find a small. The question wants you to find a bigger collection. Why should we find a bigger covering? You can always slap another thing on there. Let's see if you can find a smaller covering. Okay. And well, anyway, when you read the homework, you'll know what I mean. Anyway, so next 11, 12, and 17. So that's that. So when you get back after you finish the homework, I will talk about them. All right, now let's look at homework problem number 1 on page 175, which is there is not much to talk about, okay? The process is very straightforward. You just go from C over 2 to 3C over 2 and until you cover the thing. I removed some of the covers because why bother? Had to have so much junk in there, right? So I ended up covered by, I think, 5 or something, I1, and then there's well, whatever, I1, I0, and then 0.1, 0.2, 0.3, 0.7. And the bigger the number C gets, the interval gets as well. As a result, if we start at the end, then we don't need some of the smaller intervals. So that's how, and then I found a smaller number of covering, okay? The smallest one, well, what I did is start out with I 0.67, which covers all the way to 1.005, right? And then work my way backwards and found a few other I's, and eventually was able to cover it with a smaller number of covers. And so that's problem 1. Problem 2, a similar situation. I was able to cover this thing by 2 covers. There's I1, and then when C is, I don't know, oh yeah, C is, if we say C equals 10 to the minus 10 over 2, what is that? And then delta C is 1 minus that, okay, so then so then delta C goes from here all the way to here, which yeah, the over 2 part is so that there's an overlap and stuff. So the minimum cover you're going to need is 2 covers. One cover big, and the other cover just covers 0 or something like that. Okay, and problem 3, we need a function that is has no maximum. So immediately I thought of the function 1 over x, defining 0 to be 0, function f as 0 to be 0, then it of course has no maximum because the maximum becomes infinity. But this function, however, if you say, well, what if we need function f to be bounded? Okay, now if it's bounded, then we can do this thing right here, where it's 0 all the way till 0.5, and then it jumps to 1, but there's a hole there, so it doesn't ever reach 1. Then it goes down to 0 in a straight line. So it approaches 1, which means it has no maximum, because 1 is not the maximum in the sense that no f of x is ever maximum. Okay, so that is not particularly exciting. But problem 4 is somewhat more interesting. Now let me look at it first. So problem 4, we are working within definition 9. Okay, so we have a specific function. We're given specifically the epsilon is 0.1, and what can delta be? So that's a matter of well, I just graphed this thing. Okay, that is we'll assume x1 is less than x2 in the story. So then we need to calculate x2 minus x2 squared minus x1 squared is less than 0.1. And the question is, how big can x2 minus x1 be? We just take x2 to be bigger than x1 to be convenient. So then to do that, what happens is that we'll draw the 2 graphs. Okay, that is that's the y minus x squared less than 1 graph with all the conditions in there. That is x and y are bigger than 0, etc. And then the other one is then we graph y minus x, or x2 minus x1 is delta or less than delta, and see where it goes. Now what happens is that then once you find the equation, then y equals to 0.1 plus x squared equals to 1, okay, and you solve this equation, then you will get delta equals to 1 minus square root of 0.9, and that is the answer. I also graphed this on the calculator so you can see better. See, here's the function, right? This is in the pink area, which includes the green area. Yeah, okay. Now in this function, as you can see, that this is the area where with all the conditions, y bigger than 0, y is less than 1, etc. With all those conditions, and y is bigger than x. I have y stands for x2 and x stands for x1 because the calculator doesn't accept x1, x2. So then you have that's the one condition. So within that area, which has x squared minus y squared minus x squared is less than 0.1. The question is, what is the maximum of y minus x? Okay, so here's the delta here. So y minus x is less than delta. As you increase the delta, the y minus x line is all the way across, right? You push it up this direction. Let's see. Over here, push it. I'm pushing it the wrong way. And let's see, I can't get my hand to move the right direction. Let me stand over here. Yeah, you push it up this line. Push the y plus x line this direction up, okay, until it touches the other line. That's the maximum it can get. In other words, you increase the delta down here. The delta is the vertical distance here. And so if you increase the delta, eventually the 2 dotted lines are going to hit, and that's the maximum that the delta can be. So, and once you set those 2 equations of the 2 lines the same, then that's how I got the answer, which is correct because it's the same as the answer at the back of the book, which is you have to solve the equation. Where is it? I don't even know where it is. Okay, and so you have to solve the equation 1 equals to square root of 0.1 plus x squared, and that will give you the answer. So next, let's look at problem 11. Problem 11 is proving the intermediate value theorem for general cases, okay? That it crosses not just 0, but any old spot that's between the maximum and the minimum. So let's say that that it equals to we're gonna do that by simply figuring out what number is between maximum and minimum, and then let define g of x equal to f of x minus that number. Then use the same proof as in the intermediate value theorem in section 6.6, and the same argument will come out to be the same. Okay, that is, you end up f minus c equal to 0, therefore f equals to c. And that's the proof of problem 11. Next, problem 12, that's a list of stuff, okay? And I have it drawn in a chart here. The least upper bound and the maximum, sometimes there is no maximum, right? And then, yeah, some of the functions have no maximum, and some of them has a maximum. It really just depend on the graphs. Okay, this is the answer, which is all you need to do really, and just which almost look like I'm just copying from the back of the book. Although there is a slight difference because it has no minimum, even though it has a lower bound. Okay, because it approaches the x as an asymptote, and the same story here. And so let me show you, I graphed all these functions to prove that this is the case. Here are the graphs, right? As you can see, we need to know where it turned. At some points, we have to calculate the maximum. The only way to do that is to take the derivative, which I did with a calculator, okay? And to figure out where the maximum is and all that stuff, or the minimum or whatever. So that is the four different functions that that is and this is where I got my answers from. All right, so then, and another thing I want to specifically mention, although this is not part of the homework, is problem 12. Okay, it's something that is quite, even though the homework didn't say anything about it, I specifically want to draw your attention to this function right here, e to the power negative x squared, that I've always liked it. The reason I liked it is, look at this thing, okay? It comes from negative infinity, okay, and it's 0, 0, 0, all the way to about -3 or so. When it gets to -3, -2, suddenly it came to life, okay? So it was 0 all the way from infinity, it came near into 2 or so, and suddenly it came to life, and then it became alive, and then it dropped it, and then it came down, died, and then went back to 0 again. Now, isn't that cute? It just it's a function that if you want a function that's 0 all the way from one end to the other, okay, and then suddenly just rose to 1 for no reason whatsoever, then this is the function to remember that you might need it in the future sometime. You never know, okay? E to the power minus x squared. So if somebody asks you, is there a function that's 0 all the way, then suddenly do something, and then 0 again, and this is it. Now, in reality, it doesn't actually go to 0. You know, it's just a very small number, but it dies so fast, okay? You can't tell the difference. That is, I have some values here. See, at 3 is already at 10 minus 4, and by 4 is at 10 minus 7, okay? 10 minus, and then by 5 is at 10 minus 11. That's less than a billion. And that's how fast it's dying, like over here. So it's effectively 0 by the time it made it to 4. So the function just rise up and died. And it's like, I always thought that was very neat. And I should mention that it didn't just rise up and die, but it was dead, it was 0 from negative infinity. So from infinity unto infinity, it was 0 the whole time, except around when it got to the origin, it just for no reason, it moved. And then it just it stayed flat again. And I find that very interesting. So finally, we're going to prove the least upper bound of the sum of functions is less than least upper bound of the individual function. Now, there are only two cases, okay? The case one is if the least upper bound happens at the same spot, then of course, then they are the same. Now, if they happen at two different spots, then the least upper bound is going to be essentially going to be less than the other one, because the least upper bound of the combined of the sum function is going to be a different number that will be less than or equal to the least that will be less than or equal to the least upper bound function of the separate functions, which will have least upper bounds likely in different places. So these numbers then most likely are not the least upper bound. So anyway, and then of course an example would be, well, I have a couple examples here. I think they're obvious enough. You can just look at it yourself, okay, and make it come out. And that marks the end of this section, which is very long.